In this video, I will introduce convolutional graph neural networks. I will also briefly introduce graph attention mechanisms. Convolutional graph neural networks apply to two different scenarios. In the first scenario, we want to find representations of individual nodes in a single large graph. This corresponds to the case where we have a large social or information network and we wish to find representations of nodes with the use of the graph neural network. The second case is one in which we want to find representations of full graphs in a database of small graphs. This corresponds to the case where we have a database of chemical compounds and we want to find representations of the underlying chemical compounds. The predominant use case of graph neural networks is in the case of single large graphs, and that is the focus of this video today. Convolutional graph neural networks derive a lot of their motivation and they bear a lot of resemblance to image convolutional neural networks. In image convolutional neural networks, a convolutional operation is applied to a set of adjacent pixels in a particular layer to get the pixels in the next layer. Similarly, in a graph neural network, the pixels correspond to representations of nodes. After all, we are trying to find the representations of nodes in a single large graph. And a one-to-one correspondence exists between the neural network nodes and the graph nodes in each layer. Unlike image convolutional neural networks, the number of units in each layer is fixed to the number of nodes. Whereas in most uses of image convolutional networks, the size of the activation map varies from layer to layer. However, since we are looking at the case where we are trying to find representations of individual nodes in a single large graph, the number of nodes in each layer is fixed. This is very similar to the pixel level CNNs, where we are trying to find the representations of pixels in an image. And in the convolutional neural network in graphs, the adjacent nodes are aggregated to create node representations of each layer. This is again similar to an image convolutional neural network where the pixels, adjacent pixels are aggregated in order to create the activations of the next layer. The idea in a graph convolutional neural network is based on the principle of homophily. Homophily is a general concept that is used very often in network science. And the basic idea behind this principle is that nodes that are adjacent to one another have very similar representations. So for example, in a social network, you often have friends who are connected to one another, and they are friends because they tend to be similar. And this idea is inherited from the image convolutional network, which also assume representation similarity in adjacent pixels. After all, in an image, the values of the pixels, when they are adjacent to one another, tend to be very similar. The neural network connectivity in a graph convolutional neural network is implicitly defined by the graph connectivity structure. What do I mean by this? What I mean is that the node representation in a given layer are obtained as a function of the node representation of that node and its neighboring nodes in the previous layer. This, in essence, defines the structure of the graph convolutional neural network. And I will give a more detailed description of this in a later slide where I give pictorial representation. So first I'll begin with some notations in order to define the inputs to the graph convolutional neural network. Since we are trying to find the representations of nodes in a single large network, we assume that these representations are denoted by x1 through xn. So each xi is a vector with dimensionality d. This vector may have many different types of components. Some of these components might be application specific. So for example, there could be social network profiles or the interests of a social network actor. Or there could be structural features such as the node degrees, the node neighborhood size, and so on. So what this means is that this approach is general enough to represent both structure and content in the graph. So again, now I'll define the notations for the hidden representation in each layer. So you assume that you have a set of layers in your graph convolutional neural network, and the representation of the ith node in the kth layer is noted by HIK. So the subscript I corresponds to the node index and the superscript K corresponds to the layer index. And for each layer, a one-to-one correspondence exists between the graph nodes and the neural network nodes, which results in n layer-specific nodes. So the n is the number of nodes. So for a given layer, you have exactly n neural network nodes, which are denoted by H1K through HNK. These are the hidden representations for layer K. Now the input layer corresponds to K is equal to 0. So what this means is that Hi0 is Xi. Recall from the previous slide that Xi is the input for the node I. Now each layer might have its own dimensionality. So the representation in the kth layer are pk dimensional. And since when k is equal to 0, this corresponds to the input layer, the value of p0 is the input dimensionality d. Next, we'll define the connections in the graph neural network. So the connections in the graph neural network are inherited from the structure of the graph. This is something that I alluded to before. Now I'll discuss it in a little bit more detail and also provide a pictorial illustration. So there are two types of connections. One is the self connection. In the self connection, each node Hjk is directly connected to its corresponding node Hjk plus 1. Note that the index k is the layer index. So you're directly connecting to a node to its representation in the next layer. The second are the neighbor connections. So for each edge ij in the original graph, a corresponding edge exists in the graph from layer k to layer k plus 1. So here I have shown a pictorial example. So I have a base graph on the left containing 5 nodes. Now here I have used a directed graph for simplicity because it just reduces your number of neighbor connections. But in general, this is applied to undirected graphs. The more common use of convolutional neural networks is for undirected graphs, although it can also be used for directed graphs. So as you can see, you have self connection. So for node 1, you have a self connection to the corresponding node 1, but you also have neighbor connection. So you can see here that for each node, for each neighbor, so for example, node 4, it has neighbors, it is incident on both nodes 5 and node 3. So again, if you look at the neural network on the right, from layer K, you have a neighbor connection to node 5, and from layer K, you have a neighbor connection also to the node 3. As well, of course, you have a self connection to the node 4. So next we define the outputs and loss function for the graph neural network. Since the number of nodes in each layer remains fixed, there are as many outputs as the number of nodes in the output layer. So what you do is that you aggregate the losses over all these output nodes depending on what kind of application that you're looking at. So for example, let's say that you have the collective classification application, which is the fully supervised case. In this case, the losses are defined by the class labels, which are the ground truths at the labeled nodes. So typically you'll use a log loss or a cross entropy loss in the case of multi-way classification. In the unsupervised case, the losses are defined by the reconstruction error with respect to the input representation. So you have an output representation for the input node xi in node I. And what you do, you can take a squared loss between these two representations. And finally, in the semi-supervised case, you can use a weighted combination of these two losses. And of course, the weight are defined based on cross-validation, depending on what maximizes your classification accuracy. So once you have this neural network defined, the only thing that remains to be discussed is what are the functions that define the function from the layer k-1 to the layer k. So the hidden state for a node I in layer k is generated from that of the same node and its neighbors in the previous layer. Recall that the structure of the graph neural network was defined on the basis of incident nodes. So a node is only connected to nodes in the next layer to which it is connected. Similarly, HIK, therefore, HIK is a function of the representation of that node in the previous layer, as well as all of the nodes HJK k minus 1 that are incident on it. Now, this particular function is defined in a variety of ways, and we'll go through two or three different ways of defining this function. And by changing this function, one can design graph neural networks with varying properties. And a lot of research has been done on the choice of this function. So the simplest function that is often used in graph neural network is the neighborhood function. In the neighborhood function, what we do is that we take all of the representation of the neighbor nodes, we average them. So that's the first expression in equation 2, that you're summing up HJK minus 1 for all incident nodes from node I. Here, AI is the adjacency list of node I. So J lies in AI. You're taking all the HJK minus 1, the nodes in the previous layer, you're adding them up, dividing by the size of the adjacency list, and then you're multiplying by a weight matrix WK. This is a trainable weight matrix that is learned in a data-driven manner. And then the second term in equation 2 corresponds to the self-connection. So you take this, the representation in the previous layer, that's HIK minus 1, you multiply it with a bias matrix BK, and then you add up both the representation along the self-connection as well as along the neighbor connections. And then you apply a nonlinear activation function phi to this expression over here. Now this phi is a nonlinear activation function, and typically the ReLU is used. So one point that you will notice is that in equation 2, the first term I have divided by the size of the adjacency list. This is a form of degree normalization. So why is degree normalization used? The reason that degree normalization is used is because the sizes of the adjacency list, that's your AI, are very different for different nodes. Typical networks, they have the real world networks, they have vastly varying degrees according to the power law degree distribution. And if you do not do this, you're going to have a problem because you won't get comparable embeddings along different nodes. So that is why this type of degree normalization is important. The second operator, which is actually the most common operator in graph neural networks, the graph convolutional operator. And this is how the convolutional graph neural network derives its name. Now, the previous neighborhood aggregation operator, it uses node-wise normalization. So if I go back to the previous slide, you can see that you're dividing by the size of the adjacency list, which is node specific. Now, in this case, in the case of the graph convolutional operator, you do edge-wise normalization. So what you do is that for each particular node, you divide the embedding by the geometric mean of the degrees at the two ends of the node. So that's shown in equation 3. Now here, of course, you need only a single weight matrix WK because you're combining the self connections as well as the neighborhood connections in one framework. And again, you apply the same activation function phi over here. Now, this graph convolutional operator, this equation 3 can be represented in matrix form. And in matrix form, what you do is that you define a matrix HK whose rows correspond to the representations of the individual nodes. So that's your capital HK. And the capital HK for a particular layer is defined in terms of the HK minus 1 of the previous layer according to equation 4. Here, AC is the adjacency matrix. So you're directly using the adjacency matrix, which is obtained by dividing each edge weight by the geometric mean of the two node degrees. Remember that in the convolutional operator, you were normalized by the product of node degree. That's why you have to normalize the adjacency matrix by dividing each edge weight by the geometric mean of the two node degrees, and then you add 1 to each diagonal entry to account for the self connections. And this activation function phi is applied in element-wise fashion to the matrix argument. And this matrix form is what is very commonly used in the case of the graph convolutional operator. And the reason is that it can facilitate sparse matrix operations on GPUs. A third very common form of the operator is that of GraphSAGE. GraphSAGE is slightly different from the previous two neighborhood-based approaches, which tend to aggregate the representation along the self connections and the neighborhood connections. What GraphSAGE recognizes is that the representations along self connections are somewhat more informative than those along neighbor connections. So what it does is that it keeps them separate. It keeps separate transformations along the self connections as well as the neighbor connections. So the idea here is that you don't mask what you have already learned for a specific node by aggregating its neighbors with it. So here I've shown both the two equations. I've shown the simple neighborhood operator, which I discussed in the previous slide, which aggregates your self connections and the neighbor connections in the first equation here. The second equation is the one that corresponds to GraphSAGE. Note that here the main difference is that we are taking out the second term and we are keeping it separate. These are separate components. So your HIK in the next layer will almost always have a different dimension from the previous layer, because now you're concatenating the representation for the previous layer along the self connection to that of the neighbor connection. Now, this is of course the simplest form of GraphSAGE, where we are just using the simple neighborhood operator. In general, GraphSAGE does not use this type of simple neighborhood operator. What it does is that you can formulate in a more general way by replacing this simple neighborhood aggregation with a general aggregation operator gamma. So here in equation 6, I've given the more general form of GraphSAGE. Note that the main difference from equation 5 in the previous slide, where you have used a neighborhood operator in the first term on the right, I have replaced it with the gamma operator. Now, of course, if you use gamma to be the neighborhood operator, then you'll get the same thing as the equation 5 that you got in the previous slide. But in practice, you use other values of gamma. And the two most common forms of gamma, one is the max pooling operator, in which gamma is defined as the element-wise max over all the nodes in the adjacency list, W pool Hj minus 1. So this additional matrix W pool needs to be learned during backpropagation. The second aggregation operator that is commonly used, that is to use the embedding after applying an LSTM on the neighborhoods with random permutation. And when these were tested, they actually provide very similar results. In fact, the pooling operator provides slightly better results, and so it's more commonly used. Now, you can also handle edge weights. So let's say you have edge weights Cij associated with the edge Ij. All you have to do is to change the operator to multiply before aggregation of the hidden weights in the neighborhood operator. You multiply by Cij. And again, in the case of graph, this is for the simple neighborhood aggregation. If you were to use the graph convolutional operator, again, it's very similar, where you have to multiply by Cij. And again, the matrix form of the convolutional operator remains unchanged as long as you define your adjacency matrix in a weighted way. The GraphSAGE approach and the graph convolution network can be easily used to embed new nodes because weight matrices are shared along nodes. So it's relatively simple. So once you have a graph neural network trained, you can actually take a new node and find its representation. So what you can do is that you can simply start with the original representation of the new node and apply repeated convolutional operations to obtain its embedding. You can also generalize this approach to knowledge graphs. In knowledge graphs, you have different link types associated with the edges because you have different entity types and you have different link types. All you really have to do is to use separate matrices for different link types. So you can see here, the weight matrix W, I have WKR. So the superscript not only contains a layer index, it also contains the type of link. Your R corresponds to the index of the type of link. And you have different adjacency matrix. You can see the adjacency matrix AC, that also has a superscript R corresponding to the adjacency matrix for the Rth link type. And this is very useful in learning from knowledge graphs. Next, I'll discuss a little bit about how graph neural networks can be enhanced with the use of attention mechanisms. Now, let's do a brief recap of the graph convolutional operator, which I have restated in equation 7. As you can see, one of the weaknesses of the graph convolutional operator is that it aggregates over all of the neighborhood nodes. So you can see it's simply aggregating over all the edge minus 1 before multiplying with the weight matrix WK. But this is a potential weakness because when you're trying to find the representation of a node, not all nodes are equally important. Some nodes are more important than others. And by doing this, there is no discrimination between the two nodes when you are adding them up. So in the attention-centric model, what you do is that this hard coding degree weighting that you're using for the weights in equation 7, you say that the importance of a node doesn't just depend on the degree weighting, you want to use a learned weight. So here I've replaced the degree weighting with a learned weight alpha ijk. Now, of course, the problem with this alpha ijk, which you see in equation 8, that is that the number of possible weights scales with the number of edges. That is a problem because you can't learn that many ways. It can cause overfitting. So the way that's handled is that the parameters alpha ijk are defined indirectly in terms of a compressed attention vector AK. AK is a 2pk dimensional column vector. And the way you define alpha kij is by applying a two-layer feed-forward network, which takes the hidden units of I and j as input, and AKIJ is a weight vector in the output layer. Now, the ReLU activation function above is often replaced by the leaky ReLU to avoid too many nodes with zero activation. So this compact attention vector AK, that in terms of which you are defining alpha ijk, it is learned by using the backpropagation algorithm. And the overall effect of this attention mechanism is to learn the importance of different adjacent nodes. And by doing this, the activation flow is performed in a more discriminative manner with relevant vertices, and this results in more accurate results.